This is an Asahi Seiko coin hopper for a gaming machine, and I bought this some time ago for a project I was working on which didn't come to fruition, so it's been sitting around unused since that time. And I went online onto their website and tried to find the datasheet, but it seems to have been superseded for a more electronic model. And the datasheet had a link, but the link was dead. It didn't. It led to a picture of the hopper, which wasn't terribly helpful. And I did all the usual things when that happens. I tried changing it to PDF at the end of the URL, and no pic came up with a page header. And then I tried looking at all the other datasheets to see if there's a pattern. Nope, couldn't find the datasheet. So I'm going to have to work it out myself. So basically speaking, this is designed for British 2p coins. And you put them in the hopper, they just pour into the hopper and it will pay them out automatically when the motor runs. So looking at this, it's got the rotating drum at the bottom. And I'm going to have to reverse engineer everything to find out what the connections are, but there's 3 connections here which are probably they're connected to the coin level detectors, which basically relies on the coins just shorting brass plates out. And if I pull those off, in fact, it'll reveal more. There's a little catch you push down and then the whole thing comes off, so I'll move that out of the way. Here's the rotating plate, and basically speaking the coins drop down, and then as it rotates, when it gets round to this point, there's a couple of pins here that are sloped on one side but then a hard edge on the other, and they pincer the coin out. They push the coin out sideways between 2 spring-loaded pins, and once it's been pushed out a certain distance it pings out, but it seems to go through an infrared sensor here. When it does that, the unit is mounted on a slide out tray, as a lot of game equipment is, so if you press the catch at the bottom you can basically just slide the whole mechanism out of the machine for maintenance, and it's got this fairly chunky connector at the back. I quite like these connectors. There's this solid connector in the back they're designed to self-align, and then there's this floating connector here which is just designed to self-align that small amount that when they get pushed in it just clicks in solidly like that. It's very nice actually, I quite like that. So the connector in the back, let's see what we've got here. We've got 12 wires for a start, and it is numbered. It's numbered 1 to 10 and then 11 to 22. Oh, 11 to 20 should I say. Okay, so let's make a wee note of that and start deciphering things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. A lot of pins. So let's take a wee look at this end first for the infrared sensor. There's the infrared sensor. It's on its own little circuit board with 3 wires going to it. Black, red and white, I'd guess black and red, you can't always just assume that though, are power, and the white will be the signal back. Doesn't seem to be much in the way of active circuitry in that. Oh, this whole circuit, the whole sensor is just poked through the metal and it's held in place by one screw. Let's remove that. Oh. Try not to lose bits. Is that all that holds that sensor in? Yes it is. Okay. Little connector in the back, that's handy. There's a resistor in the back of this. There are 2 pins at one side. This is an infrared sensor. It detects the coin physically passing through it like that by the breaking of an infrared beam. It's a phototransistor. And it looks like the positive, negative, the white's the middle. It looks like the phototransistor has positive and negative connected to either side, and then the middle output pin is going to the middle pin on the connector. And then on this, with a strange but long solder joint, you've obviously just missed cropping that one, there's a resistor 221, 220 ohms. So let's see if we work out the voltage from that. The infrared LED will typically be around 1.5, 1.7 volts, somewhere in that region. And the current, I'd guess, in this application would be probably around 20 milliamps, although I'm sure these can go up to about 50 milliamps. So if we had a 5 volt supply minus 1.5 the LED equals 3.5 volts to drop, divided by 220 ohms, and we're looking from the region of about 10 to 20 milliamps maybe. 16 milliamps. That looks like it's designed for 5 volt operation. Okay, right, I'll plug that back on again. Make sure I get it on the right way. Yeah, I think that looks right. I don't think it can go another way. I think it is well keyed. Yes, it is. So I shall put that back in. Oh, where did the wires come up? I think it went like that. Yeah, that fits all right. So I shall put that screw back in. And I'm not sure if that's actually going back into an electronic module. There is, this is the motor unit, and I do actually see a circuit board hiding away in there. So I'm just going to screw this back in and line it up carefully. I don't know if there's much play, but I don't want it sticking up above this metal plate because the coins physically slide out along there, and I don't want it to hit the photosensor, otherwise it would damage it or scuff it, and that could result in it not triggering properly. That it's just held with one screw, but that seems to do the job. These are the pins that detect the coin passing. Well, they don't detect, they give slightly, they're spring-loaded. And this one's spring-loaded as well, so that when the coin actually goes through them, let's do it to them, it will push through those two pins, and pushing them apart, and then they'll spring back together, and it will fire it out with force, and flick it through the sensor at the same time. If the hopper mechanism stalls, it will actually try and run in reverse, and if it does run in reverse, those pins that actually deflect that to the side are ramped, so it will push the coins up, or if the worst comes to the worst, they'll spring down instead. So if I wind it back, you'll see that the pins have a hard edge on one side and the angle, and the spring-loaded mechanism on the other, just to allow for the coins having to go in the opposite direction. There's also a stirrer spike. It seems to have like 4 positions for stirrer spikes, but just one is occupied, and that just stirs and churns the coins up to make sure they feed down properly. To change the coin payout, you'd simply change the disc in this. They've got the smaller holes or bigger holes just to accommodate whatever coinage there is, but the 2 pence is actually one of our bigger coins. The larger one is the £2 coin. I don't even know if it would accommodate the £2 coin. I'm not sure, you'd have to go for a different unit. So let's see, I think I'll take this connector off the back, trying to remember which way around it goes. Oop. Third time lucky. I'll take a look at the connections in the back and see what's going where. I can see the red, black and white coming from the photosensor, and it looks as though it's going straight to the connector. Okay, now the first thing I'm seeing here is there's a loop between 2 connections, and that's so the machine can detect when the actual mechanism is in place. If the mechanism is not in place, this loop isn't present, and the machine can detect that the coin mechanism is missing. The 3 wires come down to the, let's actually note these down, let's tally them up to what these are going into. So these are the 2 green ones that are going to sense when the mechanism is in place, and they're in positions 10 and 20. I'll turn this round that way. So ten and 20. Okay, I'll note that down. Hopper detect. I'll just say hopper present. Loop. Hopper present loop. Okay. The wires coming from the coin level sense are going to brown, yellow and blue. So these are in positions 12, 13 and 16. 12, 13 and 16, but which is which? This one is the shortest. I'm guessing that the way that they're arranged in the hopper, that one of these plates will be a common connection, and then one will be the low-level sensor connection, and the top one will be the high-level sensor connection, which will basically just common down to just one of these plates. So I'd say I'll make the short one, I'm not sure what the official designation is, but I'll make the short one here the common. So it's actually going into pin 12, coin detect common, coin level common. This is the other low level one, so it's going to the next pin. Coin level low, and that means the other one is going to be coin level high. High. Okay. This isn't going to leave us too. Oh, the next ones are going to be the sensor going down to the infrared sensor here. So what are they going to be? Red, white and black. Are they actually red, white and black in the matching connector? Yes, they are. I notice there's two reds and blacks. I'm guessing the other one's the motor. I can actually see it now. I can see the connector here. I've got red, black, orange and green going to the motor. So that's given that it's a 24 volt motor, that means that if you mix the reds and blacks up in this, you could actually put 24 volts into the photosensor. That wouldn't work out very well. So where are we here? So that's going to be 10, 9 and 8. 8 is plus 5 volts. 0 volts is 9 for that's for the coin eject detect power, and the white one is going to pin 19, coin eject detect. Once I've got this worked out, if I can actually control it, I'll power it up and see if it can spit some coins out. So that just leaves, the power is coming from that end of the connector. So these two, the green and orange, and the red and black at the end, are the ones that are for controlling the motor. So pin 1 is 24 volts, pin 11 is, so that's a 24 volt motor, 11 is 0 volt motor, and the green and orange, I'm not 100% sure. I did see in another guide for another version of the hopper that there was a hopper motor run positive and motor run negative. I'm not sure if they're actually, there's active circuitry that you just take them to 0 volts. I'm not 100% sure, so I'm not going to chance it. I'm not going to just power it up. It's there in 1, 2, 3, 4, 5, 6 and 7. So I'll just do motor orange and motor green. Not 100% sure of their function yet. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's all the wires counted for. Now comes the motor. So the only way I can think of doing this is to pop the motor open and take a look at that circuit board. Keep these screws separate. I'm guessing it's all the big screws here. I see the two small screws in the vicinity of the circuit board, so I'm not going to take them out. They're thread locked in. So I'll just take the big screws out. Now, is that going to come out? Looks relatively promising. I wonder if I can put it upside down. Ooh. Ooh. Cogwheels. And a loose bit. Okay, let's transfer these wheels back into that other side. That's the gearing for the driving the hopper plate. What is this bit that just fell out? Oh, you know what that is? That's an end cap for the. That's to prevent the motor shaft being damaged when it stalls, because the thread can actually pull the motor backwards and the shaft backwards and forwards. So I'll put a screw back in that. It's not supposed to be out. So I'll put something back in there. It's quite a common little feature on the worm drive motor shafts. Just designed to protect the motor by physically stalling the end of the shaft if it tries sliding forwards. And this is an indent to line it up, and then the screw to hold it in. Right, the circuit board. It's got 4 transistors here and a sense resistor, so it's an H-bridge driver. Which makes sense because it is able to reverse the motor when it stalls. I wondered initially when I saw it, I didn't realise there was a circuit board in this. I thought it might have been a mechanical system they used. But no, it's electronic, and this has also got the electronic controls. So here's a wee circuit board. Oh, it's quite thick with surface mount in the back. Wee bit surprising for that era. So what's red, black? So I'm looking at these 2 pins. Is that an opto-isolator? I see what might be an opto-isolator here. Let's meter that out. So we'll use the meter in continuity. Mode, continuity beeper. So I see a resistor here. .681, 680 ohms. Is it going to one of those pins? Not really sure. Doesn't seem to. Oh, actually, I see the opti-stator is going, if this is an opti-stator, is going to the end of the resistor there. So that means that this end I would expect, if it's just a simple opti-stator, would go to one of those pins. And that means if this resistor is in series with the opti-stator, it would be to this pin? Yes, it is. I think that's all the circuitry that's involved in that input is an opti-stator and a resistor. I don't see anything else. Okay. Right, so if the orange and green are just doing an opto-isolator, I'll guess that orange is positive and the green is negative, but that might not be the case, but it can't really do much harm. Now that was 680 ohms, so what sort of voltage is it designed to take if it's 680 ohms? What current would flow? Was that 680 ohms, that resistor? I think it was 680 ohms. Let's meter it. $680 ohms. Okay, so if it was a 5 volt signal, with the case of the opti-isolators, it probably doesn't need much more than about 5 milliamps or so to actually trigger that. So where's the calculator? 680 ohms. So again, it'll be about 1.5 volts, 1.2, 1.5. So say 5 minus 1.5 is 3.5 divided by 680 ohms. 5 milliamps. That's about right. So it probably is designed for a 5 volt logic signal then. Just driving an opti-isolator in this. Right, let's put it back together then and see if it all works. So that goes in like that. I have to use a smaller driver for that one. Looks quite nicely engineered inside, but having said that, it is designed for fairly heavy duty, really smashing metal coins out and at high speed probably. I'm not sure how fast it goes, I'll find out when I power it. It is rated for 24 volts, that's what I'm going to give the motor. The motor itself doesn't seem to have much in the way of data on it, but it's probably being driven directly from the H-bridge, so I'd guess it's 24 volts. I could always start at 12 volts, but it is a 24 volt unit. So now this is going to have to sit in and hopefully it will line up with that. I'll put this connector on first. And drop it in. Seems to go in quite nicely. Not sure which screw went where, but I'm not really bothered about whether the thread lock really lines up again because it's broken now. I can always add a wee touch more thread lock later if needs be. Rightio, and I'll screw this connector back on. Goes on this way around, I think. I don't think good to get twisted. No, that's alright. Should be alright. I'll double check before I put it back in completely though. In fact, I'll double check now. There's the link. There's the plate with the 2 green wires. Yeah, that's the correct way around. So to allow for tolerance, it's got a slot at one end, but just a hole at the other, to allow for a bit of leeway in the bracket. Good connector, I quite like this connector. I guess it's probably a standard connector, quite widely used in gaming. Certainly all the old gaming equipment, the vintage Bally machines, had sort of fairly self-aligning chunky connectors as well. Makes it very modular. You can just pull a whole module out and change it, because they don't really want downtime in these machines. The connector is called a JAE DR20-4P. Okie dokie. So let's, I think that's it all together. Let's plug it back in. It really is clever the way this hopper goes in. When you put it in, it goes onto these 4 bayonet cap pins, and as you push down, it pushes this pin down, and then when you turn it, it clicks in place. But it won't be able to be turned out again unless you actually reach in and push this down before you turn it. It's a very, very neat system. So obviously this has just evolved, this design. So that's it there, and I'll put these connectors back on. And theoretically then, that should be it kind of deciphered. I should be able to work out how to drive it now. So let's put money in it and see if all the functions work. Nothing to really test the photo sensor with. So, for a start we'll test the coin detecting bit, which is the coin level common is going on to, it was the brown wasn't it, and the yellow were the 2 at the bottom, so I'll strip them. And I'll get the fluke over and just stick it, because it's got a couple of croc clips on it at the moment. And we'll just pour coins in. I should actually give it a wee blast, shouldn't I really, to see if it goes round before I put any coins in it. So let's actually give it a wee blast first and see if I can make it rotate. Now I have to find a isolated 5V source for the opto-isolator. What can I use? A couple of button cells? I wonder if one button cell would work. A 3V lithium cell. So that's the red and black and the green and orange. So I'll get the power supply on, and I'll select the 27V range and turn it up to 24V. Oops, way past it. 24V. Hopefully this isn't going to go bang. Get the polarity right as well would be quite good as well. Don't want to blow this up. It's drawing 9 milliamps at the moment, which is reasonable enough. That would just be the standby circuitry. So can I get that hopper to rotate by putting a supply across this? Let's try a button cell. I don't know if one button cell will do it, but it's worth a go. A lithium cell, so it's 3V, so it'll be, yeah, find out soon enough. Oh, that's pretty good. That's a good result. That's me just dabbing the wires across a lithium cell. Okay. Right, let's put some money in it, but we'll also dig out these wires, the brown and the yellow, which I've already stripped, and we'll put the fluke across it and see, oh, what's this screw for? Oh, you know what, there's another metal plate goes on there. Oh, stop the show, stop the show, I've fucked up. There's a metal plate goes on over here, so I'll put that in first before I do anything, I think. That'd be a really good idea. Don't know how important it is. I don't think it would have actually stopped it working. But it would be a good idea to put it in anyway, wouldn't it, really? That's better. That probably has a few different functions. Shielding the light sensor is probably one of them. So this should just drop down again and and click in. Okay, we're back in action again. So let's test it with the level sensors. Let's get these wire clippings out of the way as well. So the level sensor was these. There's the fluke. And I'll put it to continuity. And we'll hook it across the two contacts. I'm basically hooking it across the two brass contacts at the bottom here. Not sure how good a connection they'll make. You wouldn't think that coins, I suppose ultimately the coins are just moving about, so it's going to make intermittent connection at the very least. Oh, that seems to work quite well. That's alright. So what about the other wire at the top, the blue one? The coins aren't anywhere near that, but I can stack them up against it. So if I shuffle the coins over to this end, yeah, that works as well. Okay, useful to know. I guess really the continuous movement of the coins probably keeps those plates fairly clean. So that means that I should be able to pay out shitloads of coins now. Don't know what speed it pays out at. The flow of the coins is monitored by the actual game itself. It monitors the infrared sensor. It's not like there's no real intelligence built into this. So where's I've got orange and green. So this should now, if I get that coin cell, it should just fire shitloads of coins out. I'll move that back so you can see the wheel rotating. Well, you won't see the wheel rotating because it's hidden. That's quite fast. Oh, blimey, it gets every single one out. That's pretty good. Yeah, that's pretty good. Now I wonder if that will operate down at wonder if it will operate at lower voltages. Let's try it in 12 volts and see what happens. Will it still run? Oh, much slower. There it runs. Just a lot slower. I'm not even sure how to handle all the weight of the coins. But there you go, that's it. Worked out. So it turns out that orange is the positive. So I'll just scribble that in the paperwork. Plus, minus, and I'll just say opto. 5 volt. Good. That's sorted out. Now we know what its wiring is. I'll just make sure I leave that note in it for when I finally get to use this for something.